Okay, so we haven't done a whole lot as of yet, and we're still sort of in this chapter 0. We'll probably wrap it up today. We're going to see a little bit of definitions of flux and what have you that we'll see again in chapter 0.5, I'm calling it, which is the chapter right after chapter 1. Sorry for sort of the misnumbering. It's just the way I had it laid out. It's just the way I decided to do it. I think really all we've done so far is the universal law of gravitation, gravitation near Earth's surface, that is calculating for that acceleration near the Earth's surface. Let me pull it up real quick. Yeah, so there's Newton's universal law of gravitation. Note the relationships between them. The shell theorem. Remember, the shell theorem says that if an object is a shell, then it appears to another object outside of that shell just as a point mass. So if you were standing on top of the Earth and the Earth was hollow in the middle, it would be exactly the same as if you were standing on top of the Earth and it was solid in the middle. If they were the same mass. So a shell looks the same as a point mass to an object of mass outside of that shell. Talk about the superposition principle. We've done this, okay, with vectors. We did it a lot last semester, but if you're having trouble with it, then we really need to take care of that now. So if you still feel a little shaky, there are some homework problems for you to work through, and I recommend that you do that. And then we'll see it again in the next chapter, but then we're not going to see it again until the exam, which that exam isn't that far away, you know. It's really, we just have like maybe 4 or 5 class periods. I forget. I sort of front-loaded the exam. Can I see your exam? So we have 1, 2, 3, 4, 5, 6, 7 class periods before the exam. So not next week, but the following Friday will be that first exam. And that first exam will probably cover maybe up through chapter 0.5, maybe up through part of chapter 2. We'll see when we get to that. So 3-ish chapters, 3 to 3.5 chapters. Let's see, gravitation near Earth's surface. We derived this expression for the acceleration. Looked at the reasons why that acceleration is not exactly the same as 9.8. Primarily, or one of the reasons being that we have this centripetal acceleration that also acts upon sources because the Earth is rotating. And then we were coming to gravitational potential energy. And Newton developed this about the same time as he's developing his universal law of gravitation. Sorry. Okay, so first of all, let me just give you the expression for gravitational potential energy. That is, how much energy does an object of mass have with respect to an object that it's near to. So that U is equal to a negative, we'll talk about the negative and where it comes from, G_m_m over R. Now remember, I'm going to sort of do this over in a little cloud as an aside. Remember before, for gravitational potential energy, we had U equals mg times h. Now, we can think about this because G, we've already said, is big G m over r squared, right? And then we add in our m, and then we add in our h, right there. We can just sort of look at the units, and we see that the units work out correctly. Because if I take this h and I cancel out one of these, then I get G_m_m over r. So this is the same gravitational potential energy that we saw last semester when we talked about the conservation energy and the roller coaster and all that jazz. It's still the same. It's just expressed in terms of this gravitational constant, the big G, and the mass of the planet. Newton proved this like this. He said that the work is equal to the integral of f dot dr, where f here is a function of r. Remember that f was G_m_m over r squared. That's the expression for work that we saw last semester. It's just the force, the dot product of the force and the length. Listen, if y'all are not clear on, I know I'm a few new people, and if you aren't clear on what the dot product is and the integral is, maybe we should sit down for a half hour or so. But as we come upon this later, I'll explain it in more detail. So if you forgot about what the dot products are and how these intervals and all that, then we'll talk about it when it comes up. But just in short, the dot product, remember, is the product of two vectors that are in the same direction. That's the, in contrast to the cross product, which is the product of two vectors that are what? That are perpendicular to one another. So the dot product just takes two vectors that are in the same direction. Okay. So he said that our work, beginning with this definition, is FR, the integral of FR dr, and then F dot dr, the dot product of these two vectors, is F dr cosine of the angle between those two vectors. Remember, that was our definition of the dot product. If I have a vector A dotted with a vector B, it's defined as AB cosine of the angle between them, cosine theta or cosine phi. All right? And here F is G mm over r squared, and phi is 180 degrees. That the force between these two masses is down, and the angle, or the vector dr, comes radially out from the center of the planet, so it's straight out, and so those two vectors have an angle of 180 degrees between one another. Okay? If this isn't sinking in, it's not a big deal. We're going to see these topics come up again as we go along, and we'll spend a little more time on them, revisiting them. Now, if I do this integral, I'm doing the integral from a limit of r out to infinity, because I'm taking some object from r and moving it out, or from infinity, very, very far away, and moving it to the surface of the Earth. All right? Because my reference point here is infinity. That's where your energy, your gravitational potential energy, is equal to 0. Okay, so this works out. Let's rewrite this integral from r to infinity of negative g m over r squared times dr. And if I take the integral of that, it's just going to give me g mm over r. Remember, the is it that right? Yeah, the integral of that will give me g mm over r. So it's going to be g mm over r negative from my limits of integration from r to infinity. When little r is equal to infinity, that whole term is equal to 0. When little r is equal to big R, this is just negative g mm over r. And so that's equal to my work. All right? Again, these are things that we're going to see come up again as we go throughout the semester, but just sort of a little recap. We'll see these things, the dot products and the intervals, and this idea of energy come up again. All right? Sort of throwing it out there for now.
Would it be a positive GM over R?
Yeah, you're right, Beans. And actually, yeah, our negative then, it is going to be positive, and our negative actually comes about. That's a good point. I was sort of thinking that as I saw it, but I was hoping that y'all wouldn't notice it. But I didn't want to really talk about this, but we'll see it in the next chapter, that U is actually equal to the negative of the work, and that's where that negative term comes about. Thank you. All right? Y'all follow what I'm saying here? Because I have this negative here, I have infinity minus r, this should be positive. But up here I have a negative, and it's because my potential energy is the negative of the work. We're going to see that in the next chapter. We saw it last semester when we did energy, how the potential energy is the negative of the work that's being done. So it's not terribly important, but it's a good note. All right. Let's look at the escape speed. This is based on the conservation of energy. Any of y'all seen that movie, The Martian, or read the book? It was a good movie, wasn't it? Yeah, my son wants to see it, but the language is kind of bad. Do you think it'd be okay for him? He's 10. I'm not sure. What do y'all think? Logan's like, yeah, whatever. Okay.
And you said no was not to repeat it.
Yeah, it's pretty bad language, right? The Martian. Well, the book is really bad. Yeah. Right. Yeah. So it'd probably be okay. Anyway, in The Martian, he talks a lot about escape speed, how fast he has to go in order to leave the surface of Mars. The escape speed is just that. It's just the speed required for a projectile to leave an object's gravitational field. It was an excellent movie, I thought, and a good book too, though the language in the book is really bad, which is kind of funny because, you know, they were all scientists and they were all sitting around, F this and S that and blah, 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 blah. And scientists, they don't really talk like that. I don't think I've ever seen met a scientist that talks like that. Have y'all? Like me? Do I ever hear me talk like that? Or Dr. Doe or Dr. Lowe or any of those folks? Are you serious? All right. So anyway, it's the you can find the speed required for an object to leave the gravitational field. It's a pretty simple derivation, so let's just do it. We say that our energy plus our kinetic energy is equal to 0 when the object is on the surface. It has no gravitational potential energy. It has no kinetic energy. So I can say that negative g mm over r, which should be big R, that's the radius of the planet, plus 1/2 mv squared. That's my kinetic energy, that this always has to be 0. When it's on the surface of the planet, this is equal to 0, so at all times in space it has to be equal to 0. And then we can determine what must be the speed for it to leave just by solving this for v. If we solve this for v, now we're going to call this our escape velocity. It's going to work out to be the square root of 2gm over r. This is on your equation sheet, but you do need to know that this comes about from the conservation of energy. Our gravitational potential energy and our kinetic energy always have to add up equal to 0, and so our escape velocity, then we can derive it in that way. Let's do a few clicker questions from this, from stuff that we've seen already. Again, if you're not registered, that's not a big deal. I'll put the registration up again next time and get your clicker registered, and it'll post-date those clickers. Oh, we didn't do the weekend. We do that? We did that last semester, right? Like what? What was going on this weekend? This weekend, I'm sorry, I forgot today was Friday. So this weekend, we don't have much going on, actually. We're going to do shopping, grocery shopping. And we'll probably go for a bike ride. My little girl's got really into bike riding lately, so she's been all about riding around on the streets, give it up. Any other big plans this weekend? No. Studying already? Not class, huh? Yeah, I remember different equations. It's probably one of my hardest classes. We're going to do a little bit of simple differential equations. All right. Anything else going on this weekend? Kiwi bowling? What does that mean? With numbers?
Oh no. We're just gonna wait for the whole group of my friends to see if everybody can go bowling.
Oh, bowling. Just going bowling. We went bowling last weekend.
We're doing the last Friday and Saturday.
All right. Okay, let's do the concept test here. All right. Satellite orbits the Earth with a constant speed at height above the surface equal to the Earth's radius. what is the magnitude uh, of the satellite's acceleration? But we derived actually what is the acceleration at a certain height above the Earth. If you want to look back into it, it's fine. So if I am one radius above the Earth's surface, what then is my acceleration? I want to remind you, we did derive that acceleration. We got it through Newton's second law. A equals F over m, g m over r squared times 1 over m. And so this is our expression for the acceleration due to gravity. It just comes from Newton's second law and the universal law of gravitation. Not real big on derivations, but these are fairly straightforward derivations, so you could see something like this. More about that when we get closer to the exam, but you could see some simple derivations like this, where I'm just asking you to recreate. All right, doing sort of okay on this. Not great. Ask your neighbor what they put, if you like. I'm going to stop in about 5 seconds. I'll stop at 142. 142. Okay, it is a quarter. That's right, A. Because if I double r, which is what I'm doing, when I'm on the surface of the Earth, my distance is r. When I'm 1 r above the Earth, my distance is 2 r, right? So I'm doubling that value for r right here. If I double that, since it's an inverse square relationship, my acceleration drops by a factor of 4. So A is the right answer, or 1 as it is. This figure shows a binary star system. The mass of star 2 is twice the mass of star 1. Compare F of object 1 on object 2 to the magnitude of the force of object 2 on object 1. How do the forces compare? How does the magnitude on this mass compare to the magnitude of this force? All right, ask your neighbor what they put. Or turn to your neighbor and tell them what you put. Not everybody at once. All right, I'll stop in about 5 seconds. 115, 115. Looking pretty decent on this. He is right. Remember, with the universal law of gravitation, F is g m over r squared. Both masses are represented here, and so it should lead you to believe that, well, each mass will feel the same force. That's also a representation of which of the 3 laws in Newton's laws? No, the 3rd law, right. Yeah, it's not accelerating, so the 2nd law, the 3rd law, that I have equal and opposite forces. That if I have a force on this one, I have to have an equal and opposite force on that mass. Or somewhere there must exist an equal and opposite force. The planet has 4 times the mass of the Earth, but the acceleration due to gravity is the same as on the Earth's surface. The planet's radius then must be what? So the mass of this planet is 4 times that of the Earth, but it has the same acceleration due to gravity. Okay. We'll go to about 105. Ask your neighbor what they put. Only about 5 or 6 of you, well, now 9 of you have the right answer. 105. Okay, good. D is the right answer. This goes back to that relationship that my acceleration due to gravity is gm over r squared. So what we're saying is that the mass of this planet, this mysterious planet, is 4 times the mass of the Earth. So in order to give us the same acceleration due to gravity, we have to have twice the radius. So that would give us a 4 in the numerator and a 4 in the denominator. So 2 is correct. Excuse me, D, or 4, is correct. All right, rank these in order from largest to smallest in the gravitational potential energies. We have these collections of masses. I have a 2 unit mass, 2 unit mass, 4 units apart, all the way down to 4 unit mass, 4 unit mass, 8 units apart. Rank them in order of their potential energies, their gravitational potential energies. That is the absolute value, so we'll just get rid of the negative and just ask ourselves, what is the potential energy for each one? Good way to approach a problem like this, you might just want to write out the gravitational potential energy for each individual pair, and then you can rank the numbers. Remember that gravitational potential energy is Gmm over R. U is Gmm over R. What's that? It's not R squared. That's the coulombic, or that's the force between masses. Does it say R squared on your equation? Oh, maybe. That's for the force. They look very similar. I understand they see between two. So, when you write out their potential energies, you can just leave out the G. It's a common factor in all of them. So you can just do Nm over R for each one. All right, I'll stop at 235. Just guess if you don't know. Looks like most of y'all done pretty well. Is A right? Yeah, I think A is right. So we can just write out the gravitational potential energy. So Nm over R, that would be like 2 times 2 over 4. That's 1. This would be 1 times 1 over 1. That's 1. 1 times 1 over 2. That's 1/2. 1 times 4 over 4. And then 4 times 4 over 8. Let's see, this is 2, and this is 1. So E has the biggest one. So that gets rid of this one and this one, followed by D, B, and A, which are all the same. So that tells us number 1 is the right answer. And then C is the smallest with 1/2. Of course, those numbers don't have units because we've left out the G there, but it gives us a relative ranking of the gravitational potential energies. Okay? Just sort of recap what we have so far, because we sort of have a lot of equations that look similar, but we start with the universal law of gravitation, Gmm over R squared. All right, and that was Newton found this by the shell theorem. He showed that this was true by the shell theorem, or rather, never mind, just forget that. Rewind. And then also the acceleration due to gravity is gm over r squared. And then we also have the potential energy, gravitational potential energy, which is negative gmm over r. So those all look very similar for good reason, because they're all related. They're all sort of derived from one another. But just try to get those straight in your head. They're on your equation sheet, but you still need to have them straight in your head once in a while. Okie dokie? Okay. Let's do a couple more. The gravitational force between two objects of masses m1 and m2 separated by a distance r is which of these statements describes that force? All right, I'll stop at 1 minute. 1 minute. Okay, good. C is right. It's proportional to r squared. That's that the force is gmm over r squared. It's an inverse square law. It's an inverse square because it's spherically symmetric. That these the gravitational field lines, which we'll talk about soon, they go out in a spherically symmetric way. And whenever we find spherically symmetric things like that, we'll find that we often have an inverse square law, which we'll see with electric fields as well. All right, the value of g at the height of the space shuttle's orbit is which of these? What is g at the height of the space shuttle's orbit? Is it 9.8, slightly less than 9.8, much less than 9.8, or exactly 0? Space shuttle's pretty high up. I don't know exactly where it orbits at, but it's at least Earth radius or more. Does anybody know how high it is? But it's pretty high up. All right. I'll stop at 105. 105. This is our last one, I think. Okay, good. C is the right answer. Remember, we have this inverse square relationship that my acceleration is gm over r squared. So any increase in r, my space shuttle, here's the Earth, my space shuttle is right here. The Earth has a radius r, and then that space shuttle is an additional distance up. So any increase in that distance causes the acceleration to decrease of the quadratic, so because of that 1 over r squared. So it's much less than 9.8. But you might say, but you're weightless in the space shuttle, right? Is that what you were thinking, those of you that put exactly 0? Is that what you were thinking? Huh? Well, you're basically weightless. All right, but that's different from saying what is the acceleration due to gravity, because I can be weightless here on Earth, right? What is to be weightless? What does it mean to be weightless? Why are you weightless on the space shuttle? Right, yeah, because it's falling at the same acceleration as as your weight. So like, remember all those elevator problems that we worked? What happens when the elevator drops at 9.8 or 10 meters per second squared? Your normal force is 0, so you feel weightless. When your normal force is 0, that's when you feel weightless. So your shuttle's in free fall, constantly in free fall, and that's why you feel weightless. But the acceleration due to gravity still has a non-zero value. Alrighty. I'll post these on the website, on the concept test part of the website. Just remind you where that is. So if you go to your website under concept test, I'll post it under chapter 0. I'll make a little mark there for chapter 0. Alrighty. I have a little bit left in this chapter. Let's look at fields. A field gives the force per some unit. So a field is just some force per some unit. And you can have different types of fields. Like, for example, we'll deal later with electric fields, and in this chapter we'll deal with gravitational fields. But you can have other types of fields as well. But we're going to look at gravitational fields, and a field is just a way to measure a force per some unit, per some unit. So for example, for gravitational fields, it gives the force per unit mass. We use field lines and equipotential lines are surfaces to describe the field. So let's say, imagine that this is the Earth. I can map out what the force looks like. So let's say that I have an object that's right here. The force towards the Earth is, say, that vector. If I move it out further away, the force is a lot smaller. Because as I move further and further away, the force gets smaller and smaller. So we need some way to map out how this force looks around this object of mass. Some way to map out the gravitational force. And that's really all that we use fields for. It's some way to represent the force that an object feels. Okay, field lines are just a way to map out the force that an object feels, either due to a mass or, as we'll see in the next chapter, due to an electric charge. That's really the reason that we're doing this now, so that we'll see it again in the next chapter for electric fields. But the same is true for gravitational fields, and actually they behave exactly the same. So the direction of this force, we're going to use field lines to represent them. I'm going to draw my field line in the direction of the force. So my field line looks like this. I can draw other forces in other places, and it'll always look like this. So I can represent field lines all around this body of mass, and they'll look like this. So those field lines point in the direction of the force, and in some way we need to represent the magnitude of the force. Let me write that down first. So the direction of the field lines gives the direction of the force. We'll see this repeated again next chapter. The magnitude of the force is given by what? Now, my force is really big here, my force is smaller here. So as I move out along these field lines, my force gets smaller and smaller. What about the field lines changes as I move out radially from the source of mass? But something else about the field lines that changes. They're divergent, right? They get further and further apart. So when I have a small force, my field lines are going to be far apart. So see here, how those two field lines are far apart. Now you can draw any number of field lines, but it's still going to be true. So for example, if I also drew a field line here, these 2 points would still be farther apart than these 2 points. And similarly, the force here is going to be small, the force here will be big. So the magnitude of the force is given by the density of the field lines. All right, so the direction is given by the direction of the field lines. The magnitude is given by the density of the field lines. If the gravitational field is force per unit mass, what is that? It's a quantity that we've seen. If the gravitational field is a force per unit mass, what is that? What is a force per unit mass? What is a force per unit mass? That would be like what? F over what? Right, F over kilogram, or F over m. What is that, F over m? It's something that we've seen before a lot. Right, it's acceleration. So whenever we talk about G, G is a way to measure the Earth's gravitational field. It is a measure of the Earth's gravitational field. So it's something that we're really familiar with. It's something that we've seen, the acceleration due to gravity. That is a way to measure the Earth's gravitational field. All right? So it's a representation of that field. So the magnitude of this is represented by G. Because G is F over M. It's a force per unit mass. Now, we can also use equal potential lines. Equal potential means equal energy. And if I have an object, say, right here, is there another position where that object has the same amount of gravitational potential energy? I have that object at that point. Is there a position where that object has the same gravitational potential energy? There is a position. Where is it? Right, anything with the same radius. Because remember, my gravitational potential energy is G_m over r. And so anything with that same radius r will have the same energy. Now I can draw an equal potential line, but as Cody pointed out, it's not just a line. It's a surface. It's actually a 3D surface that comes out and around the entire sphere. So you can imagine, here have the same gravitational potential energy, over here the same energy, over here, as long as my radius or my distance from the surface is the same. So that's called an equal potential line. Do y'all have the lab yet? Yeah, so y'all did this, right? You drew field lines. Those were electric field lines that you drew. You also drew equal potential lines. Now you talked about them in a slightly different way because we talked about them in terms of volts, right? Which is also a way to draw equal potential lines. And you talked about the fields in terms of newtons per coulomb, which is a force per unit charge. We'll see that in the next chapter. All right, so that's my equal potential line. I'm going to call it an EP line. All right. Again, we'll come back to this. We'll look at more complicated structures with charges because you can have all different types of charge structures. And we'll look at how to actually calculate what is that electric field to regular sources. We'll do some volume integration and stuff. It's kind of fun. All right. Now, this is all sort of leading up to Gauss's law, which we'll see again after chapter 1 with regards to electric charges. But Gauss's law is for gravity. And the first thing we need to define is what is flux. Well, in short, flux is equal to our gravitational field. Remember, G, that is a measure of our gravitational field. Our gravitational field times the surface area. I'll show you what I mean by that, but let me just sort of finish this train of thought. We're going to use the Greek letter phi for flux, and we're going to make this a little more specific, not just G times the surface area, but it's going to be the integral of G dot n. These are both vectors. Actually, n is a unit vector. I'll draw it with a hat. times dA. All right. What this is saying is that I want my field lines that are perpendicular to my surface area. That's what that dot product is that I want field lines that are going in perpendicular to my surface area. And then this dA is some measure of the surface area. Let me break that down for you. So dA represents the surface area, and here I take the dot product because the field lines must be perpendicular to the dA. We'll see that again later, okay? So if that doesn't sit well with you, that's okay. We're going to see it again next week when we look at Gauss's law and how it applies to electric fields. And we'll get into a little bit more detail about what these mean. But just in short, let's just sort of stick with that definition. And in fact, mostly in this chapter, we're just going to use this much simplified definition that is just going to be the gravitational field G times the surface area. And I'll do several examples to show you how this works out. Now, Gauss's law says that the flux is equal to negative 4 pi G times the mass inside a surface. We're going to call this surface a Gaussian surface. And it's going to be an imaginary surface that we draw around a certain object. And then we'll be able to say, well, all the mass that's inside that surface that I've imagined, this Gaussian surface, will times 4 pi and G will be equal to the flux that's coming out of that. Let me do some examples. I have a few minutes. I can show you 3 simple examples. And then we'll wrap up this chapter. And again, we're coming back to Gauss's law. So if you feel like we're sort of left some off, we'll come back to it and treat it more rigorously in chapter 0.5, which is just on Gauss's law. So we can apply Gauss's law to several different geometries pretty easily. I mean, we can apply it to any geometry, but we can apply it to these 3 geometries pretty simply. The spherical geometry. So imagine that I have a mass of a certain sphere. This is my mass. And then I imagine that I have a Gaussian surface. So these are spheres, but I'm drawing them as circles. So this is my Gaussian surface. It has a certain area. It's a sphere. It has a certain radius. I'll just call it R. What is the surface area of a sphere? Does anybody know? No, that's the volume. Yeah, the surface area. Four pi r squared, right? It's 4 pi r squared? Yeah, that is what it is. So the surface area of a sphere is equal to 4 pi r squared. I think I put that on your equation sheet. It's not one that people often know. Let me just double check that. Yeah, so here's the area of a sphere, a cylinder, and a square, all of which we'll use. The surface area of a sphere is 4 pi r squared. All right, so what Gauss's law says is that G times the area is equal to negative 4 pi G times the mass inside. All right, so I can calculate then what G should be here. If I know what that mass inside is, it's going to be negative 4 pi Gm over my area, which is 4 pi r squared. Unfortunately, this works out to what we had found before, that G is equal to that negative Gm over r squared, because my 4 pi is canceled there. What this means is, we'll see this is a little more useful for electric fields, but what this means is that if you can measure the flux at some point above a mass, then you can measure that mass. Right? We talked about the Grace mission, NASA, they have that pendulum that goes around the Earth. That's what they're doing. They're just measuring the flux, the gravitational flux around the Earth. When you measure the acceleration due to gravity, that is the flux. Or that is the gravitational field. And then the flux is that field times the area. All right? So that's a spherical symmetry. We can also do it for a cylinder. Like say, for example, you came upon a cylindrical planet out there and you wanted to know what its mass was, right? That's not too far-fetched because there are big, long, cylindrical things in the universe that are big and we want to know the mass of them. Well, if we can measure the acceleration due to gravity by, say, looking at stars and how they rotate around it, or other objects and how they're affected by its gravity, then you can figure out what is the mass of that long cylindrical structure, which could be, I don't know, like a big molecular cloud or some superstructure in the universe. So a fairly useful thing to look at cylindrical geometry as well. Cylinder looks like this. I would imagine, I'm just imagining field lines that are coming out like this, that are not going out the ends of the cylinder. So this would be like a very long cylinder, so that the ends are not important. The ends just sort of add a little bit of a complication, which we're not going to deal with. All right, so my cylindrical structure, I can draw my Gaussian surface. My Gaussian surface is also a cylinder, shares that symmetry, and the area of this Gaussian surface is equal to 2 pi times r times the length of that cylinder. And then just like we did before, we can say g times the area is equal to negative 4 pi g mass inside the Gaussian surface. And we can solve for g is equal to negative, solving this for g is negative 2 gm over LR. So notice if we lived on a cylindrical planet instead of a spherical planet, our acceleration due to gravity would be quite different. It wouldn't be a 1 over r squared difference, it would be a 1 over r difference, or 1 over r relationship for our acceleration due to gravity. Again, it seems a little far-fetched, but it's not uncommon to find cylindrical structures in the universe or even in the lab. And then let's look last at planar, and we'll wrap it up. Flat structures, like, for example, in the early universe, there are these huge flat structures that people have theorized or even seen evidence of. So this is my flat structure. My field lines here are going to come straight up like this, out of the flat structure, and then I can draw a Gaussian surface above, and then if you can imagine below as well, this one's below. All right, I have these Gaussian surface, a rectangular surface. I'm going to say g times the area equals negative 4 pi g mass inside. And I'm actually doing twice the area here because I have both the top and the bottom, and we'll just let that area be length times width, or we'll just leave it as area actually. If I solve for g, it works out to be negative 2 pi g mass inside divided by the area. So you see here that g is not dependent upon how far you are away from the mass. Which seems interesting, right? Like if our planet was instead of flat, the Earth was indeed flat, and some people think it is even today, the gravitational acceleration would not depend upon r. It wouldn't matter how far away you are from the planet, your gravitational acceleration would always be the same. Alrighty, folks? We'll see this again in chapter 0.5, dealing with electrical fields. I think we're out of time now. Have a good weekend, okay?